Hello, my preprint of our latest paper with Tony Ikonen and Kai Rajala. It's a great moment to introduce you to one of the amazing spaces that appears in this paper. In this paper, we prove the Coarea inequality for monotone Sobolev functions on metric surfaces. I'm not going to get into details of any of them, but that adjective monotone means maybe the Coarea inequality does not hold for non-monotone Sobolev functions. And that is in fact the case. And we illustrated this in paper by constructing a concrete example of a metric surface and a function on it that is not monotone and does not satisfy the Coarea inequality. So that space in itself is very interesting, and you don't need to know any of the words that appeared there to understand this construction. All you need to know is to recall how one constructs countersets. So you start with a square in R2, and you remove the four, you restrict to the, you pick up four subsquares in the four corners. And then inside each square, you repeat this. The counter set is the set that will be inside these tiny squares all along the way in the infinite reiteration of this process. So that's just to begin with. And what you do then is, we want to construct a surface X that is sitting inside R3, and with some interesting geometry that will be described in my construction. So to begin with, first you imagine that you start with a plane, say, lying horizontally in R3. Say it's the XY plane and z equals 0. Now, in the first iteration of the counter construction, you pick these four corners, but what you do here instead is actually, instead of choosing them, you cut these. So you cut these out, and then you elevate them higher. So you bring these squares up into a different plane, say that is parallel to the original plane. So you have this wall that goes down here and joins the plane, the original plane you had. You have this wall on this side, the vertical one. So this becomes a cylinder. It has no volume inside, it's just the walls. And you repeat with the other ones as well. So you just cut these four squares and you lift them up along with the walls. So you can imagine that it's made of, this plane is made of dough or something, pizza dough if you want. And then once you pull on these subsquares and lift them upward, the dough also comes with them, creates the four walls along it. So I'm obviously not perfect in sketching, but of course I leave it to your imagination to construct the space, because you will need that imagination now or later. So far all we have is the plane, all of this is included, and then these walls, and then the top. And the top you can leave open, or you can imagine there is actually, it's also filled. The top is also filled. Yeah, that's actually more consistent with what I'm going to do next. So this is still, let's say, homeomorphic to the square, the original square you started with, because topologically nothing has happened. You haven't introduced new holes, you haven't introduced ruptures, you haven't glued anything extra, you just have stretched the space. As I said, the example of the dough is perfect here. Now, what you do next is, given that I just mentioned countersets, what you do is, now in the counter construction, inside each of these squares, you put these 4 little ones. You cut them out. But what you do here is you just repeat the construction that I just did. So you cut along these and then you raise them. You bring them up to another level. So this goes to another level. This goes to another level. Also expectedly, you do shorter elevations each time because you don't want to get to infinity too fast. So you cut these 4 squares. Of course, they're so tiny, they look like circles, but pardon my poor drawing. I always joked in my undergrad classes that if I was good at painting, then I wouldn't be a mathematician. But that's your next step. So again, it's just the walls and there's no volume inside, and these are also filled in. The caps you can see are filled. Okay, if you can do it twice, then you can do it 3 times, and if you can do it 3 times, you can do it infinitely many times. So inside each of these squares that look like, you introduce again the 4 squares and you elevate them up. Already here my cylinders are so thin that I have to basically draw just straight lines, but each of them is a tube. And let's say you go 1/2 and then 1/4 and then 2 to the 3rd and so on, so that you don't go to infinity in elevation. And what happens at infinity? What happens at the end of this construction? All that happens is that you will end up with a plane. Sorry, not that plane. You will have a plane again at elevation 1, parallel to the original plane, and you will have the counterset here and there. It's just a dust-like thing. That's the best I can do. And each of these cylinders, not just one cylinder, but each collection of cylinders, you go, for example, you pick this cylinder first, and then this one here, and then this red. Every one choice of the cylinders will end up or will hit one counterset. So in limit, these tubes lead to the counterset. Okay. We add the counterset to the collection of tubes, and that is analogous to saying that we add the cap back ultimately at infinity. So remember the first construction I said you can imagine that let me point with the green. So I said that if you add the cap and close it off, it's just homeomorphic to the square. So with the infinity, it takes some little bit of proof, but you can show that this x together with the counterset on top is again homeomorphic to the square. In finite steps, as I said, you just put the cap and it's exactly the square. You can prove that in limit also this homeomorphism is preserved. So it's the collection of cylinders plus the top cap to close it off, and that makes it homeomorphic to square. This was important to us because we wanted to ultimately find a metric space so that topologically it's homeomorphic to the squares, so that we call it a metric surface rather than just a space. It's a surface emphasizing the two-dimensionality of the thing. But wait a second, what is the distance here? The distance here is just the path distance, which means I have extensively talked about curves and length of curves and things like that. So you first of all think of x as sitting inside R3, and then the distance between 2 points on the space is the length of the shortest curve that connects them, or more precise will be the infimum of the length of curves that start at x and end at y, and of course travel only within the space x. Okay, so that makes it. And then locally, Hausdorff-2 measure is finite. That if you have a compact subset of this x, it has finite H2 measure. That is because if you are not away from Counterset, it's basically a manifold, and that's obvious. And around the Counterset, I will explain actually a few more things. Then after those modifications, this will also be obvious. Okay, what else about this surface? Not much, but for the purpose of the paper, we have to work a little bit more, or rather we have to add some twists, literally, to this space. So what are the twists? One of the things that we do is that we add spirals. Oh, no, we don't add spirals. This won't make sense. So we spiral up with the cylinders. So these vertical cylinders that I had, instead of just going straight up, maybe you, so this is this removed square, you want to go move up instead of going straight up. So maybe you do some twisted thing. So it's still a tube, but it twists and winds up until it gets there. What is the purpose of this? So that the length of tubes add up to infinity. So that when you start at level, say 1, by the time you reach level 100, you have added a lot of length, and in infinity, this goes to infinity. So what happens as a result of this? As a result of this, if you have a curve with finite length, it either has no point from the counterset on the very top. The counterset is kind of the end of this space. So either it picks no points from there, or it is a constant curve. That means if it hits the counterset, it has never left it. And the reason is exactly because of this infinite length along the spirals. So if you are at some single point in the counterset, of course you cannot move between countersets, it's just totally disconnected. The only way to move from one point to another is to travel down a little bit, to come down to some level, and then travel along another path to the other one. But because of this spiraling thing, from any point in the finite steps to this last one, this point in the counterset, the length is infinite. So it's infinitely long. So there is no way you can reach any point of this counterset C. So there are continuous curves, but none of them has finite length. This counterset sitting here is basically not reachable from any other part of this space. And for us, this implied that the upper gradient, if you happen to know about this stuff, which is kind of the derivative of a function of any Sobolev function, can be taken to be 0. So the minimal upper gradient, for example, will be 0 on this C, at least almost everywhere. So that means you don't need any derivative along counterset C, because there are no path going there. Upper gradients is a real valued function which acts as if it was the modulus of the gradient of the function. But again, I don't want to get into the details of Sobolev functions on metric measure spaces, but just about around this space. Now, the last thing I want to mention was this H2 is locally finite, and we said it's obvious away from the counterset. How about the counterset itself? So to make this work, we can say that we again go back to our construction, and we require that tubes be very thin, especially as you approach the counterset. So this thinning will decrease the surface area of the tubes, and you can make them as small as you want, because surface area is like scales like square, but the length scales linearly, right? So except for the attaching parts at the ends of the tubes, you can squeeze the middles to very, very thin tubes which have very small surface area. And they also spiral, but that increases the length way faster than it increases the surface area. So all of this you can make, and then you have this space with some nice properties. The last thing we did in the paper with the space was to actually have C a fat counterset. And the fat counterset cannot be done in this completely iterative process. In each process, you have to increase or decrease this amount of space you remove, so that at the end you end up with a counterset with positive H2 measure. And we needed this to be able to give a counter example, because along this counterset C we saw that the upper gradient is 0, but we wanted some other quantity to be not 0, and for that we needed this. So there are many variations of this construction. You can knowing examples is a must in research, and according to what you need, you always go back to them and modify them and cook up new things. We give references in the paper to other resources where they had done such similar constructions before, including Coarea, who is one of the authors, and to work of Piotr Hajwasz and Zhao Dan for some other not necessarily related to this kind of stuff thing. But yeah, so here's a beautiful example of how Hausdorff measures work, how length of curves matter and things like that. And the good thing about this is it doesn't take super advanced stuff to come up with such beautiful examples. And as I said, I have covered a lot of Hausdorff measures, length of curves in separate chapters, so these examples serve to convince you that they are useful things, and they do appear quite naturally in geometry and analysis. Okay, if you have any questions about this space, if any part of the construction wasn't unclear, please ask in the comments. I tend to read them and I reply to them pretty fast. Yeah, if you have other twists to add to this, that will also be interesting. Until my next video and another beautiful metric space example, have a good one, and please subscribe if you are watching this. Thank you.